Good afternoon, folks. How are you today? We are in week number 8. We have finished half of our semester and we have covered 5 topics. Before I start on a new topic, let's see what we have learned so far. So, in our first topic, we learned how to solve one equation in one unknown. And prominent methods we looked at was Newton-Raphson method and secant method. And what we did in both these cases is we used either the slope or we used a line connecting 2 points, as in case of secant method, doing an interpolation. So in both these cases, we were linearizing the function in some form in solving it. And this is a very, very powerful technique because imagine now we have a black box, which is our function. So we've put in x and out comes f of x. So even though you have been practicing on very simple algebraic terms or equations, but think of this function, it could be an engineering subsystem, something that you are designing. And now what you're doing is think of x as a dial. So you have a single dial with a single needle output. And what you're trying to do is you're trying to turn the dial and set the value of f to some desired value. Now you could set value of f to 0 or to some extreme value or some mean value and so on and so forth. So remember in Calculus 1 when you took a course about functions and you learned about extreme value theorem, mean value theorem, indirectly we have built it into our system. So now we can do everything to a single one equation, one unknown, or one function, one unknown, one variable system. Then we learned, so this is all that you learned pretty much in Calc 1. And we took about 2 weeks, and now you have a similar power, but you can solve even functions that are not necessarily analytical. Then the next thing we learned was linear algebra. So we learned how to solve a size n system. So we know A, we know B, we want to find X. So think of this linear system again as a box. And in this box, you have inputs X1, X2, on and on, and Xn. And of course, inside you have your matrix A, which could be stored in form of, say, A inverse. And then you feed in some matrix B. And we have our X value to satisfy. So we check whether AX is equal to B or not. So here you learned basically that conditioning of the system is very important. So you wanted a determinant of the normalized matrix, its magnitude to be as large as possible. So essentially we did a lot of matrix algebra and we learned how to solve a linear system. And the key thing there was, even though we are solving small systems using A inverse, when we get to large system, don't forget that Gauss-Seidel method. So once we learned these two things, next we went on to learn about Taylor series. And here is where I showed you that Taylor series can also be used to derive Newton-Raphson method. And again, here I want to emphasize you. So we did a very simple example. We said we are feeding in A, and our method gives us square root of A, right? So here was our function. Remember, we are feeding in X. It gives out Fx. Now, once we have chosen our problem, what we are doing is we are using our method here, right? So this is how it uses our function. So once we did this, I showed you that you can in principle use Taylor series to do anything. So you can feed in theta and your method spits out sine theta to certain precision. Okay. Okay, so on with this, two things. What we did was combine the ideas of how to solve one equation in one unknown and the idea of linear system, combine these together, and now we can solve a system of non-linear equations. So we know f, we want to find x. And this is what you did in your last lab. And you learned really very, very powerful system, because to be able to solve a system of nonlinear equation until about 20-25 years ago without computers would have been very, very difficult. But now that computers are easily available, we can solve such kind of problems. And I hope you are able to identify nonlinear systems in your courses or projects and utilize the method you have learned here to solve it. But the main thing we did after this is we utilized these ideas of linear algebra, solving a system of equations in curve fitting. And we learned both how to fit a linearized curve as well as how to fit some special nonlinear curves. And again, the key idea was that we take a nonlinear equation or nonlinear curve, linearize it. So we linearized it, fitted our least curve here, and then transformed back our solution to the nonlinear domain. So far we have been working with just functions. Again, before I go on, curve fitting. So this again, you have learned very powerful techniques. I hope you get to use these kind of curve fitting for data that you gather in your projects or labs. So the next thing what we want to do is, if we have a function, what we want to be able to do is, we want to be able to integrate it, and we want to be able to differentiate it. Once we learn these two techniques, then we can form any equations that involve the function, its derivative, and or the integral, and we can set up what are called differential equations. So again, we are going to learn, you have learned some integral techniques. Here, today we are going to talk about numerical integration. Also, if you want to impress your friends, you can say you're doing quadrature. So that's another name for numerical integration. So what we want to do here is we want to evaluate a definite, proper integral. So we want to integrate a function of x with respect to x. So that's our integral. Let's see what we mean by definite. Definite means we have limits, both specified, a and b. And proper basically means proper as opposed to improper, means that a is finite, b is finite, and function of x is also finite in the range ab. So this is our closed interval when we use square parentheses. That means both the boundaries are included. So what does this integral mean? So if we plot this function, let's say this function looks something like that. Let's say this is limit a, this is limit b. Then this area under the curve is this integral value. So that's what you learned in your Calc 1, Calc 2 courses. But there is another way to look at integrals, and that is to look at averaging function values. So if you think about it, the area under this curve, so we are integrating this between a and b, so this blue curve, blue area is what we want. So what we can think about it as, this is an area same as width times some average function value or height. So this mean value, so as to say m. So we can think of that as now the rectangular area. So this pink area or red area is same as this blue area. So what we think about f average is that we are averaging f with respect to x. So we integrate f with respect to x and x itself, dx itself from a to b. So you can see it becomes same idea here. So one way of, instead of thinking of areas, is that integration is basically finding averages. Once you think about that we are trying to find average by integrating, so we are just normalizing it by width and then integrating the function. So when we divide the area by this width, this interval, we get an averaged function value. So now you can think that you need averages, or you use averages in many, many places. So this would be an excellent place to use numerical integration whenever you want to find averages. And the key thing you will find out throughout this topic is that basically our integration scheme would be taking weighted average of function values. So again, this idea of average comes again. Okay, so let's see why we want to learn numerical methods to integrate, especially when you probably spent more than half the semester about integration techniques. Well, the integration techniques you learned in your calculus courses can integrate only a small number of functions. Many functions are not integratable. So for example, let's suppose we want integral of e to the minus x square with respect to x from some limits. So this is not integratable analytically. So all we can do is we can do numerical integration. Secondly, instead of given a function of x in this analytical form, we might be given a function in tabular form, and then we might be asked to integrate it over a certain range of x values. Then again, you cannot use your analytical techniques. Another thing could be that the function may be embedded in hardware or software. So all you can do is you can feed it an x value and get the function value out. So again, you cannot use any analytical techniques. And of course, last may be that the function is a very complicated function and you don't want to spend the time integrating it. All you want is a approximate integral value. So you can see we have a lot of reasons to use numerical methods for integration. So what we are going to do is we are going to learn a method called trapezoidal rule, which you probably already know, but we are going to look at it in detail. We are going to look at the truncation errors involved in it, round off errors involved in it, and then that how that error analysis can help us develop other methods such as Richardson extrapolation, Romberg integration. And then you are going to learn another method called Simpson's one-third rule. And finally, a method that has not been talked about much in textbooks, but now that again we have computers available, we can use this Gaussian quadrature very meaningfully in a very productive way, in a profitable way. Okay, so let's see our first method, trapezoidal rule. So again, let's look graphically. X, f of x, here is our function. We want to integrate between a to b. So what we do is we divide this whole interval into equal width strips. And their width is equal to h. So we number them 1, 2, on and on and on. And last strip number is n. So we have n equals width strips. So obviously you can see that h is going to be b minus a over n and vice versa. N is going to be b minus a over h. So this is our strip width. So what we do is we consider one strip. Let's say strip number I. So notice if we start numbering our points, say A is x1, x2, x3. So the last one would be xn plus 1. So strip I is between xi and xi plus 1. And let's say that's our curve. So what trapezoidal rule says is we connect these two function values fi and fi plus 1 by a straight line, and we say the area of the strip is approximately this trapezoidal area. So area of strip I is this trapezoidal area, and you can see it'll be height times average function value. Average function value is sum of the two function values divided by 2. So that's our one strip area. But we are interested in total area. Total area would be area of first strip, area of second strip, on and on to area of nth strip. So we know that our area of I strip is here. Each one has a factor of h by 2. So we take that common. So our first area would be f1 plus f2. Second one would be f2 plus f3. And on and on and on. Last one would be fn plus 1. So you can see all the interior function values appear twice, but the end values appear once only. So the end values have weight of 1, whereas interior values have weight of 2, and we are doing a weighted function sum. Right? So our total area is therefore f1 plus 2 times sum of all function values from 2 through n, and then last function value. So another way of looking at this, as I just told you, was this is a weighted function sum, function value sum, where our weights are 1, 2, on and on, and 1. And we have a multiplier up front of h by 2. Okay, so let's see what we have done. So graphically, we want to integrate this function between a, which we are calling x1, and b, which we are calling xn plus 1, because we want to have n strips. So when we have n strips, we will have n plus 1 x values. And then what we do is each strip we approximate by a trapezoid and find the trapezoidal area and add them all up. So you can see the trapezoidal areas add up pretty nicely to area under the curve. Sometimes our trapezoid is overestimating the area, sometimes it is underestimating the areas. So hopefully this overestimate, underestimates cancel, and this trapezoidal rule becomes a decent estimate. So let's see how good an estimate it is, looking at a numerical example. So let's suppose we are given our function in a tabular form. So we are given at x equally spaced 0.1, 0.2, 0.3, 0.4, 5, 6, 7, and 8. And here are our function values. Each one is known to 3 decimal digits. I really would appreciate if you'll do this example along with me and not depend on the slide. And that way you will get a feel for numbers also. Okay, so here is our table. What we want is, we want integral from 0 to 0.8 of this function with respect to x. So we just saw in trapezoidal rule, we use weights 1, 2, 2, 2, and then 1. So what we do is we do a weighted function sum. So we multiply 1 times 1, 2 times this, and on and on and on, and total it up. So when we sum it up, we'll get 24.538. So remember, our formula for area was H. You can see H is 0.1. So H by 2 times the sum. And we will get 1.2269. So this is area using a strip size of 0.1 and trapezoidal rule. Let's see how good it is. So it turns out that the function we had was e to the power x. So all I did was wrote e to the x, rounded up the decimal digit, third decimal digit. So if we integrate e to the power x from 0 to 0.8, we will get e to the 0.8 minus e to the 0, which is going to be 1.2255. So this is our true value. So the actual error we made was, or true error, actual error is 1.2269 minus 1.2255 is 0.0014. Okay. So notice we are matching 1, 2, 3. This rounded up would be 7. This rounded up would be 6. So 7 versus 6, this would be uncertain. Right? So we have 3 correct decimal digits or 4 significant digits. Okay, let's look at error in trapezoidal rule. So we call this truncation error, and you will soon see why. So now consider again, we have that one strip, ith strip. So this is xi, this is xi plus 1, this is x-axis, this is our function axis. So this is fi, this is fi plus 1, this width is h. So when we approximate with the trapezoid, we are underestimating by this amount. So that is what is called our truncation error. So let's, for the time being, assume that this was some derivative. So when we integrate, what we do is we integrate the function from xi to xi plus 1, right? So when we integrate this function, we get this area under the curve. So let's suppose if our function was dy dx, then dy is fx dx. So if we integrate both sides from xi to xi plus 1, this would be yi and yi plus 1. So when we integrate it, we'll get yi plus 1 minus yi. So what this says is, if we have a corresponding y versus x curve, whatever shape that might be, this is our yi, this is our yi plus 1. So this difference in height, this difference in y values is represented by this area. So we are going to utilize this idea to do our error analysis. So let's expand yi plus 1 by Taylor series. So we'll get yi plus h times yi prime plus h squared by 2 yi double prime plus h cubed by 6 3 factorial yi triple prime, and let's say we have higher order terms. So what we can do is we can subtract yi from both sides. So we'll have yi plus 1 minus yi is all this residual value. Okay. Now remember, we defined our function was dy dx. So this value yi plus 1 minus yi, if we replace dy dx by function, we'll get h times fi, h square over 2 times fi prime, h cube over 6 times fi double prime plus higher order terms. So this is my equation here. Now let's take fi plus 1 and expand it by Taylor series. So we'll get fi plus h times fi plus h squared by 2 fi prime, h cubed by 6 fi triple prime, so fi double prime, and higher order terms. Right. So what we are going to do is, from this equation, did I make a mistake? Oh, this is single prime, double, triple, sorry. From this equation, we are going to extract out this quantity. So we'll write h times fi prime is fi plus 1 minus fi minus h square over 2 fi double prime. And actually, I'm not going to expand this. This is all higher order terms. Higher order terms. Okay. Then what I'm going to do is I'm going to take this h times f prime and I'm going to substitute this equation here. So what would we get? We'll get yi plus 1 minus yi is h times fi. And remember, this is h square over 2 fi prime. I have here h times fi prime. So h by 2 would be left over. And I'm going to write this right-hand side equation. So that was just this part, right? And I still have that left. Okay. So this is our area of the ith strip. And if I simplify this, I will get h by 2 fi plus fi plus 1. I combine this with this quantity, I will get minus h cube over 12 times fi double prime plus higher order terms. So there'll be combination of higher order terms. We can say hot combo. So this is what we call truncation error. So this is our trapezoidal estimate, and this is our truncation error. Truncation error in ith strip. So what we do is, since we don't know what this higher order terms would look like, just like we did before, we will say ETI is minus h cube over 12, and this second derivative we'll find at some zeta I. We don't know what the zeta I is. All we know is zeta I is on strip I somewhere. So therefore, if we knew zeta I, we will know the true error. But we don't know zeta I, so we don't know the true error. But before we just look at one strip, let's look at all the strip, total error. So of course our area is area of first strip, second strip, so on. So same way we can add up the truncation errors. Every truncation error has this term h cube over 12. And then we have second derivative, let's say zeta 1, second derivative zeta 2, on and on and on to second derivative x zeta n. So what we can do is we have the second derivative value. For most functions, probably the second derivative values don't vary very much. But what we can do is we can say, let's suppose this is n of these second derivative values evaluated at some zeta average. All we know is zeta average is between A and B. So that would be our error, actual error. Except we don't know this zeta average value. So what we are going to do eventually is we are going to find out what is the largest magnitude of the second derivative, and that will become our error bound. But the key idea to learn here is, notice since n is equal to b minus a over h, our truncation error, let's call it bound, will become, so if you multiply here by h, b minus a over h, we will get minus b minus a times h square over 12 times second derivative, and we can say whatever is the largest value, right? But the key idea here is that the truncation error is proportional to h square. So we did our analysis. We said our function was e to the x. So remember our true value when we integrated from 0 to 0.8, that table. We got our true value. 1.2255. Remember our trapezoidal estimate was 1.2269. So our actual error we found was difference of this 2.0014. Now let's see what our error estimate would say. So our truncation error bound would be, we throw out the minus sign, so we'll have 0.8 minus 0 times h square, 0.1 square, over 12. And now notice, if function is e to the x, function prime would be e to the x, function double prime would be e to the x. So the derivative value maximum would be wherever x is maximum, that is e to the 0.8. So we will get 0.0015. So this is our absolute error bound. And it makes sense because this is greater than our actual error. So we are bounding the actual error. Okay.